Okay, instantaneous speed. We looked at instantaneous speed way back when we were talking about average speed. And we know that instantaneous speed can be measured using either the radar gun that officers use, or let's say you go to the amusement park and you're testing out your pitching arm, your ability to throw a baseball, how fast you can throw it, the radar gun, or using the speedometer in a vehicle. So those are two ways in which we can calculate the instantaneous speed. The speed at that one particular moment in time, at that very instant. Okay, so think of it in that way. So when you glance at the speedometer while traveling in a car, what you see is the speed at that particular instant. Whether this was the speed earlier in the trip or not does not affect the current reading. So whatever the reading is at that moment is what the speed of the vehicle is. So instantaneous speed is the speed at any particular moment in time. So let's look at here this object. We talked about uniform motion or constant speed. So we look at now distance, time. Last class we were looking at speed versus time with regards to uniform motion, constant motion. So the object here is increasing its distance over time. Calculate the average speed of the following graph. So to do that, we'd have to calculate the rise and run. But here we have a distance time graph. So if we calculate the slope, let's say, of the following, right? We take any 2 points. Right? Take any 2 points. We have the rise, right, which is our change in distance. Our run, change in time. This will help us calculate our average speed. So, according to this graph, our average speed is 10 meters per second. So, which means here, over the entire trip, they're going to be going at that rate. Okay, that average speed. Now, on a speed time graph, a constant speed is shown as a horizontal line. So, what I've drawn here, showing this slope the way it's shown, is the same information that I have drawn here. However, we have here a speed versus time graph. So one is plotting the distance over the time. This one is plotting pretty much the speed over time. And what information can I be able to pull out from this? And we could do that, yes, but the acceleration, because it's a speed versus time graph. So pretty much, if it was traveling at 10 meters per second, right, as its average speed, then what we're saying was that it was traveling consistently at 10 meters per second every single second in time. So distance time graphs versus speed time graphs. So both graphs show the same information. Notice the difference. If we found the slope here of any 2 points, we have our delta D, delta T. This would allow us to find the average speed. But if we took any 2 points and we calculated the rise and run, what is our slope on a horizontal line? 0. So the slope is 0. But what does the slope calculate on a speed time graph? Exactly. Slope is equal to the average acceleration on a speed time graph. So if the slope is 0, what does it tell us about our object? There's no average acceleration, which means what? Is there movement? Yes, there's movement at a constant speed. So the object's not going any faster. It's going consistently at 10 meters per second every single second in time. It's not increasing the speed. So that speedometer is not changing. It's staying where it's at. Which means if it's not changing, what else can I find now at any point on this graph? Think about the topic. Exactly. Because if it's not changing its speed, the instantaneous speed is going to be, can be calculated, can be taken from any one of those points. So anywhere along this horizontal line, we can extract the instantaneous speed because the object is traveling at a constant speed. So it's traveling at a constant speed. It's not accelerating. We're not increasing time or our speed. We are not decreasing our speed. We are going at the same rate throughout. So what happens if the object increases speed at a non-constant rate? So however, if you want an accurate instantaneous speed from a distance time graph, you need to take the time interval, make the time intervals small. Mathematically, this is done by drawing a tangent to the curve at a particular instant of time. So a tangent pretty much is a straight line. We find a point, and with a ruler, we draw a straight line, and we calculate the slope of what we call that tangent line. So we find one point along the curve. So we find a point along the curve. We don't just take the 2 points, let's say here. We don't take these 2 points. We don't take these 2 points. What we do is we look along this curve, and we create these tangent lines. And we calculate the slope of the actual tangent line. So depending on how you draw it, yours might vary with the person next to you, depending on what kind of an angle you get it. And of course, you want to be able to draw a big enough graph so you can draw a more accurate tangent line. Because the smaller the graph, the harder it'll be to really get an appropriate tangent line. So make sure when you're graphing that you graph and give yourself, the graphic space. Question?
No, you answered it.
Answered? Okay. So, recap. On a distance time graph, instantaneous speed is the slope of the tangent to the curve at that moment. On a speed time graph, the instantaneous speed is read directly from the line on the graph for that moment. So remember, when we drew it, at that moment, we could pick any point. Whatever that point is, that's the speed at that moment. But on a distance time graph, you are drawing pretty much a tangent to the curve of your line. So if we look at this, what is the instantaneous speed on this? On the instantaneous speed on a speed time graph. This is a speed time graph. We just take the actual point. So it says the instantaneous speed at 1 second is, what is it? 10 meters per second. And at 3 seconds, it's 30 meters per second. So that's the instantaneous speed at those time markers.